camera calibration lab with Ridley.
I'm Cameron.
And I'm Daniel.
The objective of this lab was to learn how to calibrate and correct for lens distortion of a camera and calibrate its spatial frequency response.
Distortion occurs when image magnification varies with field height and pupil position. Positive distortion or barrel distortion occurs when the actual magnification becomes less than the paraxial magnification with increasing age. As a result, the corners appear pushed in towards the optical axis. Negative distortion or pincushion distortion occurs when the actual magnification is larger than the paraxial magnification with increasing age. As a result, the corners appear to be pulled away from the optical axis.
We started lab by setting up the Thorlabs camera on the table. There were two lenses used in this lab, one with a focal length of 16 millimeters and another one with a focal length of 4 millimeters. The shorter focal length lens introduced more distortion into the images. We were able to find the sensor size and pixel dimensions online. The half-inch sensor format has a sensitive area of 6.66 millimeters by 5.32 millimeters, and the pixel dimensions are 5.2 microns. We measured both of the horizontal and vertical fields of view of each lens using a standard 8.5 by 11-inch paper and filling the field of view of the camera. Knowing the size of the paper and how far away the camera, we calculated the angular field of view for the low distortion lens to be 21.21 degrees by 16.69 degrees, and for the high distortion lens, 66.76 degrees and 60.93 degrees.
We measured the shape of the box by initially taking a photo of the box showing two of the faces with checker patterns. Importing the image and running the compute extrinsic function, we selected the corners of each face and extracted the grid corners. The software calculated and output the rotation matrix for each side. The last column shows the normal z vectors, and by using the dot product and an inverse cosine, we can get the angle between the two faces. We calculated approximately 89.5 degrees. We would expect there to be a 90-degree angle, so the percent error in this is 0.56%, which falls within the tolerance of the paper taped to the box, not being exactly flush with the box surface.
We then use software to calculate the spatial frequency response, or MTF, of slanted edges taken using the 60mm focal length lens. By placing the target in locations such that the target fills the FOV of the lens, with this orientation achieved, the slanted edge response is calculated and plotted using the SFR mat2.m MATLAB program. Selecting a small region of interest at each slanted edge, we were able to see the MTF of each slanted edge in the center and at each corner of the target.
Started with the lens with less distortion. Using the checkerboard board, we optimized the field of view of the camera and adjusted the exposure time and focus for the best image results. We took 20 photos of the checkerboard at different orientations. Here's an array of all of our images, as well as the extrinsic parameter plot, which measures object position and orientation for each of the 20 images. Then we ran the images through the calibration toolbox, starting by selecting the four corners of the image and extracting the grid corners for the entire range. For the low distortion lens, the software found the grid corners fairly accurately, and it was not necessary to enter a predicted distortion value. Then we ran the calibration function and analyzed the results. Initially, we got a pixel error around 0.3, and when analyzing the reprojection error, we saw outliers specifically on image 2. To improve the results, we recomputed the corners on image 2. After redoing the corners on image 2, we got a pixel error of 0.287. It was difficult to improve and refine the pixel error any further beyond this value.
We replaced the low distortion lens with the high distortion lens and took more images using the checkerboard cube. Again, we ran the images through and attempted to extract the grid corners. However, this time inputting the initial values for the distortion coefficient was necessary to align the grid corners. This step was repeated several times until the red marks were well aligned with the actual corners on the checkerboard. The images on the left has no distortion coefficient, and the image on the right, the inputted distortion coefficient where the red marks are much closer to the corners than before. This was repeated for every image, and once all the images were complete, we ran the calibration function. The focal length was calculated to be 4.01 millimeters, which is extremely close to the actual focal length. Initially, we got a large pixel error that we were able to reduce by recomputing the corners on outlier data and suppressing a few of the images. We ended up with a pixel error for the high distortion lens of 1.05 and 0.59, and below are the distortion coefficients that were calculated. The first term is the main distortion term, the second term is the fourth order distortion, and the third and fourth terms are tangential.
We then remove distortion from the system by utilizing calibrations that take into account distortion introduced by each lens. With the software properly calibrated, the images are restored back to their original undistorted state. The unique nature of distortion as an aberration is that it does not introduce any blur to the image, which makes it possible to correct for a majority of the distortion using software. If the images were in perfectly sharp focus and in high contrast between the dark and broad regions, it would be possible to have a much lower pixel error, which result in a better corrected image.
Then calculated the percent distortion for both lenses using the data outputted from the calibration. We calculated the low distortion lens to have about 1.5% distortion and the high distortion lens to have about 50%.
Here are some examples of the images being corrected using the 4mm fisheye lens.